Okie dokie. Well, it doesn't look like we have anyone here right now. Sorry, move around. And that's fine. But I am going to go ahead and get started doing some questions. I did get one email this week asking us to talk about a continuity problem, namely the question, which function is continuous? At x is equal to 0. And we were comparing 2 over x times 2x plus 3 log x squared over x squared plus 4 over sine of x, and x plus 1 over cos of x. So we can start by, some of these can be essentially just eliminated. In order for things to be continuous, we need to, like if we're looking at a graph, we need to be able to like see there's a continuous line there. But if we want to break it up very specifically, we want the function at that location to exist. We want the limit of the function to exist. Sorry, the limit of f of x as x goes to a. F of x as x goes to a, we need that limit to exist. And we need those to be equal to one another. And the reason that we have this rule is so that we don't have a function that looks something like this. Because this is not a continuous function, even though f of a exists and the limit exists. They're coming at the same location from the left and from the right. But because those two don't equal one another, it's not a continuous function. So things to watch out for are asymptotes. What do asymptotes look like? Well, if we have a vertical asymptote, it might look something like this. Or more specifically, I'm going to say it's going to look something like this. This actually this, where x is equal to 0 at 1, is a function that is a log function. Here we have a vertical asymptote where x approaches 0, but never actually gets to 0 as it extends into infinity on the y, negative infinity on the y-axis. So we know by looking at this that if I were to take the log of 0, I would essentially get a do not exist, because while we can take the log of like, 0.000001 and it'll be something very, very large and very, very negative, the log of 0 is essentially a deity. So we know that based off of the fact that we can't take the log of 0, essentially because it just goes into negative infinity, we're going to say that log of x is not continuous at x is equal to 0. Another thing that we can't do in terms of the domain of functions is divide by 0. That's going to give us something that, again, DNE does not exist. So we need to think about what do we have that ends up being divided by 0. When x is equal to 0, x squared over x is going to be 0 over 0. but we can actually, theoretically, we would be able to simplify this into just x, right? It's x squared over x. I'm not sure if that's what they want us to do, though. I don't think that's the answer here. I might have to get back to you on that. But we can also track down other locations where there is a 0 over 0. For instance, over here in, if we were to have a graph of sine of x, sine of 0 is equal to 0. So this would turn into 0 plus 4 over 0. And we would end up with divided by 0, which means that that's outside of our domain. We can't have that happen. If we were to look at cos of x, we would have something that looks like this, right? And this is good. We're allowed to do this because at 0, cos of x is equal to 1. So we're good there. That's not the condition that makes this impossible. Another place that we can look for 0 over 0 is if we were to look over here, we have 2 divided by 0 times 0 plus 3. So that's 0 because we're multiplying it by 0 here. Because again, when x is equal to 0. So that is no longer in the running. Finally, this, I believe, is the answer right here, because it is continuous. We're going to have to do a double check for all of these rules here, though. Basically, I think what we're going to do is we're going to say, let's break it down like this. We're going to say that we have f of 0. If this is f of x, then this is going to be 0 plus 1 over 1, which is equal to 1. Then we're going to say we have the limit as x goes to 0 of x plus 1 over cos x. And that is also going to equal, if we remember some of our limit practices going on, x is approaching 0. This is going to approach 1. So we know that we have f of a is equal to the limit as x goes to a of f of x. So we know that we're in the clear here. This should be a continuous function. Did I copy that down correctly? I did. All right, let's see what's happening here. Let's maybe think about this one as, we'll do f of a, or rather f of 0. Oh, here we go. F of 0. F of 0 is going to end up equaling 0 over 0. For 2 minutes. We still theoretically would be able to cancel that out, turning that into x. So f of 0 would be 0. And the limit as x approaches 0. Should also be 0. Which is what I don't get. Okay, this would also be a complete. Okay. Also equals. So theoretically, this would also be a continuous function. The answer is definitely the bottom one. I'm going to seek a graph to check this out. And I'm going to select this function. And let's see. Okay, should be able to see this now. No. Oh no, duh. Okay, so the domain, of course, is going to be x is in the reals, except when x is equal to 0, because I can't just cancel out that x, because I'm being a bit of a doofus, it seems, today. X can't equal 0. We can't just simplify this out. That's not how this function works. We can do that when we're doing our limit, but unfortunately, this function doesn't exist where x is equal to 0. So yeah, we still have to consider that as being divided by 0. Okay. I hope that makes things a little bit clearer. So the idea being that this is not true, is lives growing up, because f of 0 is going to be equal to, doesn't exist, because again, we're dividing by 0. The limit exists, but f of 0 doesn't. So we fail to be able to apply two of those conditions of continuity. So that's kind of what we're looking here at this continuity question. Okay. So this week we kind of did a couple of sections. We did 3.1 and we did 3.2 and a bit of 3.5. So if I can find chapter 3, we can get started on some of these questions. And that was a continuity question, I believe, from last week. Because that's when we were talking about limits and continuities, if I am not mistaken. Okay, so we're going to do a couple of like basic preparation for derivatives. We are going to be in section 3.1. Again, unfortunately, the numbers might not match up because I still don't have the current edition of the book. But hopefully you'll be able to just see what problems we're looking at here. We're going to do problem 1, where we have y is equal to 3x. We are going to do problem, we're going to do problem 6, where y is equal to x to the 4/3. And we are going to do problem 10, where f of x is equal to 1 over x to the 4th. And then we're going to do problem 19, which I'm going to kind of squish in here, where y is equal to root x. So all of these different problems are going to be using the power rule, which is the initial formula for differentiation that we're going to learn. And the power rule essentially says that if I take the derivative of something, say I have the derivative with respect to x of some number that is x to the n, then this is going to be equal to n times x to the n minus 1, which you can see put into practice in something like number 1, where we have, we're going to make this dy dx, which is the same thing as y prime, is going to be equal to 3 times, and then I'm going to take the derivative of this x. This is a constant. So this is going to be times, this is x to the 1. So this is going to be 3 times 1, and then there's no more. It's essentially, you know, x to the 0. And so that's going to be 1. This is just going to end up being 3 because we just have that one x there. Okay, so now we're going to look over here. Here we have x to the 4/3. So dy dx is going to be equal to 4/3 x minus 1, which I'm going to write down as 4/3 minus 3/3. That's how I like to do it with the fractions. You can keep track of what you're looking at. So I would say the answer to this question is 4/3 x to the 1/3. Okay. Moving on, here we have something that's a little bit different. This is 1 over x to the 4th. So this x to the 4th is not exactly where we're used to it being. The way that we solve that is we use some of our rules of exponents, and we say that x to the 4th is, or rather x1 over x to the 4th is equal to x to the -4th. That's just the way that exponents work, is that if you want it in the denominator, you can use the positive number. If you want it in the numerator, it's just the negative number. That minus there essentially means 1 over x to the 4th. So I'll rewrite this as f of x is equal to x to the -4, and then I can go ahead and do the same thing. I can say that f prime of x is equal to -4x, and this is not going to be to the -3. I'm going to do again -4, and then I'm still going to subtract 1. So this is going to be -4x to the -5. Or if you want to write it like this, it'll be -4 over x to the 5. And either of these answers would be considered correct. Okay. And finally, over here, we have y is equal to root x. Thinking to yourself, probably, how can this be a power rule? But we're going to do something similar to what we did over here, in that we're going to say that root x is actually equal to x to the 1/2. And now that we're able to write it down like that, it's a fairly simple process of saying that if y is equal to x to the 1/2, then y prime is equal to x, or rather 1/2 x to the -1/2. 1/2 minus 2 halves is -1. So you could write it like that, or you could write it as 1 over 2 root x. All of that works, essentially. So yeah, basically there's just a lot of problems in this section where we're breaking down things in this way. One important thing to note, we're going to do a couple of the more complicated ones. First off, if you look at something like number 11, which looks like this. It's just a line. That's 6x cubed plus 4x squared minus 2x. And then I'm also going to look at number 21, which looks like this. For number 11, basically the rule to remember here is that the derivative of a sum is equal to the sum of the derivatives. So I can just say that this is the derivative of 6x cubed plus the derivative of 4x cubed squared minus the derivative of 2x. So I break it down. I know that dy dx is going to be equal to the derivative of 6x cubed, which is going to be 6 times 3x squared, plus the derivative here, which is going to be 4 times 2x, minus the derivative of 2x, which is just going to be 2. And that is going to be my answer. I'm allowed to just add all of those derivatives up, which is really handy. Finally, over here, we just have a little bit more simplification to do. We say that this is going to be equal to root x to the negative 3. And this is going to be x to the negative 3, and that's to the half. And our rules of exponents say that if you have the exponent of an exponent, you can multiply them together. So this is actually going to be equal to x to the minus 3 halves, which is going to turn out to be y prime is equal to minus 3 over 2 x to the minus 5 over 2. So we're just combining here the square root and the 1 over x is equal to x minus 1. Oops. Okie doke. Next, we're going to think a little bit about exponential and logarithmic functions, which we can see in 3.2. Basically, the thing to remember here is that there is a difference between exponential, where I have some number to a variable, 4 to the x, e to the x, 108 to the x. All of these are exponential functions, versus a power function, which looks like x to the 2, x to the 108, or 180, x to the n, essentially, where n is some number. So here, in a power function, x is in our base, and here in an exponential function, it's in the exponent. And that's the difference between these two. So if you have a problem that looks like number 2, which is f of x is equal to 2e to the x plus x squared, you're able to solve it by saying, this is my exponential function, the derivative of 2e to the x is equal to 2e to the x. And then I'm going to add to it the derivative of x squared, which is going to be 2x. So that is my f prime x. And again, this in the red is based on the rule that the derivative of e to the x is equal to e to the x. And another way that we can think about this is the derivative of e to the kx, where we have a constant up here, for instance, e to the 2x. We're going to be able to bring that constant down, and that is going to be equal to k e to the kx. And those are just two different rules that we kind of experienced in this. And we can get in next week into why this is, specifically this e to the kx rule, and as well as the rule that states if you have the derivative of some number where a is some number that is not e, then you're going to end up with the natural log of a times a to the x as your derivative. Again, all of those can be explained next week using the chain rule, but for now, you just get to use these as rules. We can go ahead and do problem go ahead and do problem 5, where we're going to be able to use this rule, where we're looking at y is equal to 5 times 5t plus 6 times 6t, or 6 to the t, excuse me. And then we're also going to do number 12, where we're looking at f of t is equal to e to the 3t. So for number 5, the important thing to recognize here is that you can't just combine these and say this is 25 to the t. It's not how it works. We're going to consider this to be a constant. So this is going to be 5 times the derivative of 5t, which is going to end up being 5 times, as we set up here, this is 5. So this is going to be 5 times the natural log of 5 times 5t. And then we are going to do plus the exact same thing. This is 6 times the derivative of 6 to the t. So this is going to be plus 6 times the natural log of 6 times 6 to the t. So I would write our final something like this. Noting that 5 and the natural log of 5 are both constants, and then we have our variables in the exponent of that 5 and that. Same with 6 and the natural log of 6, those are both constants. Then over here we have f of t is equal to 3 e to the 3t. Here we're going to be able to use this rule. So f of t, if our k is equal to 3, f prime of t is going to be equal to 3 e to the 3t. And the differences between this and the power rule is that we're not subtracting 1. We're just bringing that 3t down and we're leaving it be. It's always going to be subtract. And we're not removing, we're not like taking it and then moving the 3 down so that it's 3 times e to t. It's always going to be e to the 3t. We're just going to continually take that 3 down. An example of what I mean by continually is that if we were to take the double derivative, which we're allowed to do, if we were to take the second derivative here, f double prime of t would be equal to 3 times 3, so 9e to the 3t, and so on and so forth. So that's kind of what we're looking at here. We're also going to want to do a quick review of the natural logs. So we are going to do let's do problem 24 and 26. So again, we get to break these up. This is a constant, so this is just going to be our prime is equal to 3 times the derivative of the natural log of q, which is going to be 1 over q. So r prime, or dr dq. The reason I'm using these interchangeably is because I hope that you guys realize that they are interchangeable. Use whichever one you'd like. Dr dq is more explicit in saying this is a function of q, and this is the derivative of r taken with respect to q. So this is going to be equal to 3 over q. And then over here, we have y is equal to t squared plus 5 ln t. This is going to be the derivative of t squared plus the derivative of 5 times the derivative of t. Again, 5 is a constant. We're not taking the derivative of that. It's just attached along for the ride. This is easy. This is the power rule. We just did this. This is going to end up being 2t plus 5 times the natural log of t, which is, or the derivative of the natural log of t, which is going to be 1 over t. So our final is going to be dy dt is equal to 2t plus 5 over t. Okie doke. Let's wrap up with a couple of problems from 3.5. Again, we're just basically thinking about what kind of rules are we given here and how can we incorporate those rules into solving some of these problems. Here we're dealing with sine and cosine functions. So I'm going to go ahead and write down some of these rules. The derivative of a sine function is going to be equal to cos x. The derivative of cos x is going to be equal to minus sine x. I don't think you will require to know any other trig functions, which is really nice. Don't need to worry about those. But these also contain what if there is a constant in here. So this is going to be the derivative of sine with a constant is going to be equal to the constant on the outside, the cosine, and then the constant is still on the inside. And it's the same thing here. Here we have the cosine of a constant times x, and that is going to equal constant on the outside minus still. We've got the sine, we've got the constant on the inside still. So those are kind of our rules that we're going to be using. In the dark red, the more general rule, and in the red, we've got a what if we have a constant in the middle here. Again, that can be explained next week using the chain. So we're going to do, let's do problem 2, where we have y is equal to 5 sine x. Let's do problem let's do problem 11, where we have y is equal to a sine of bt. And over here, let's do, can't do that one. Gotta be sure that we're not doing stuff from sections 3.3 through 3.4. Let's do 14. Where z is equal to the cosine of 4 theta. Okay, so for number 2, pretty straightforward in that we have a constant times a function. This is going to be 5 times the derivative of sine x. We know that the derivative of sine x is going to be cos x based off of our rules. So this is going to be 5 cos x. That's y prime. Over here, again, we have a constant. So y prime is going to be equal to a times the derivative of sine bt. So this is going to be a times, we have a constant, we pull that constant out, then it's going to be cosine, and it's still going to be bt in there. So this is going to be equal to ab cos bt. Finally, over here, we're going to be looking at cosine. Here we have a constant in the interior. So this is going to be dz d theta is equal to the derivative of this is going to be minus sine 4 theta, and then we're going to multiply that by 4, because that's the constant on the inside. We're going to end up with minus 4 sine 4 theta is equal to dz d theta. And that's kind of what we're looking at here. So basically, the important things to remember in this section are the power rule, your exponent rules, your logarithm rules, and then your rules for sine and cosine. And to know what to do if there's a constant thrown into the mix, and you should be good to go. If anyone has any questions during the week, of course, feel free to email me, and we can talk about it in next week's session. And to everyone watching, I hope you have a wonderful week. And have a wonderful week. Thank you.